SIMS stands for secondary ion mass spectrometry. It's a technique that allows the detection of trace amounts of a species in conductive samples with a sensitivity in the range of parts per million or even down to parts per billion. We can use SIMS to map out the distribution of these species. So we can do both X and Y. So it's basically a mapping on the surface or on one layer. But a more common application is to measure the distribution of your species in a Z direction. So with this, SIMS is a perfect tool to, for instance, study diffusion. Another way of using SIMS is to simply measure a mass spectra, which allows to determine which kind of species or elements you find in your sample. With the SIMS at MiNaLab, we can detect almost all elements, including hydrogen, but excluding noble gases. The SIMS at MiNaLab has two different ion sources available. We have one oxygen and a cesium ion source. Depending on the elements you would like to study, you have to choose one or the other, which depends on the chemical properties of the elements. This primary ion beam is then directed onto the sample surface, where it sputters but also ionizes simultaneously both atoms from the bulk material but also from the species of interest. These ions are then accelerated and going through a mass separating system, and then we have three different detectors where we can detect the currents of each species of ions. So we have an electron multiplier detector, which has a very high sensitivity. If we are above the range where this works, we can use a Faraday cup. And the last one we have is an MCP detector. An important application of SIMS in semiconductor physics is to study impurities in materials. So those impurities can be incorporated unintentionally, coming from the process itself, or they can be incorporated intentionally, for instance as dopant or during diffusion studies. The way we analyze impurities is that we first take mass spectra to check which species are present, and then in the second step we take depth profiles where we pick out species we are interested in and then track their distribution in Z direction or depths of the film. If we have reference samples, so samples where a known amount of the same species is, for instance, implanted with an ion implanter in the same bulk material, we are also able to quantify the amounts of the species. So one typical application for this is diffusion studies, where a sample is annealed in an atmosphere, for instance hydrogen or deuterium, and then after the first annealing we measure the depth distribution, and then in consecutive steps anneal again and follow up how the distribution evolves.